Next, we want to look at common factors and greatest common factors. So we've already talked about how we can make a list of all the factors in a previous video, and as you see here, I've got the list of factors for 8 and 20 listed out. Common factors would be any factors that are on both lists. So 1, 2, and 4 are factors of 8 and factors of 20, so they're common factors. The greatest common factor is exactly what it sounds like. It's the biggest number on both of those lists. So in this case, that would be a 4. We want to find the greatest common factor of 24 and 60. What we're going to do is we're going to try to think of something that we can divide both 24 and 60 by and end up with an integer result. So no decimals when we divide out the number. So 24 and 60 are both even, so they're both divisible by 2. I'm going to make sort of what looks like kind of an upside down division sign here. I'm going to put the 2 off to the side to show that I'm dividing by 2. 24 divided by 2 is 12, and 60 divided by 2 is 30. And then I'm going to repeat that process again. 12 and 30, they're both divisible by 6. 12 divided by 6 is 2. 30 divided by 6 is 5. And when I try to think of something that divides 2 and 5, the only thing I'm going to come up with is 1. And I would kind of get stuck in a loop where it would keep dividing out of 1. So we usually don't write that we're dividing out of 1, since it doesn't change that result. Once I've broken the numbers down as far as I can by dividing them out, the numbers that are left over, when I find their product, that gives me the GCF, the greatest common factor. Now, as you saw when we got down to 2 and 5 and we couldn't divide anything else out, that actually has a name. That's called being relatively prime. So, for example, the numbers 12 and 5 are relatively prime. If I tried to think of something to divide them out, the only thing I could divide them both by is 1. So when there's no common factors other than 1, we call them relatively prime. Next, I want to find the GCF of monomials. That works a lot like the example I showed you a moment ago. First, I'm going to focus in on the numerical part. So in this case, that would be the 18 and the 28. 18 and 28 are both divisible by 2. 18 divided by 2 is 9. 28 divided by 2 is 14. Now, I did not divide out any variables, so all of these variable pieces are still there. Now 9 and 14, they're relatively prime. There's no other numbers other than 1 that I could divide out and not get a decimal. So now I'm going to move on to the x's. The first term, even though it's not written, know that it has an x to the first power, and the second one has an x squared. So I can divide out an x because they both have at least one x. And then when I divide out the x from the first term, x divided by x is 1, so essentially it like cancels out, and all I'd have left would be the 9 and the y squared. Now for the second term, when I do x squared divided by x, I'd have 1x left over. I'd also still have the 14 and the y squared that I didn't touch yet. Now they don't have any x's in common in these two terms, but they do both have y's, and they actually both have a y squared. So I'm going to divide out a y squared. Y squared divided by y squared is 1, so it's sort of like they cancel out, and all I'd have left in the first term is the 9. And same thing in the second term. Y squared divided by y squared is 1, so it's like they cancel out, and all I'd have left over is the 14 and the x. My GCF is all of the things that I divided out multiplied together. So 2 times x times y squared, or 2xy squared, that is my GCF.